We have a lot of symbiotic bacteria that live in our gut. Are there any symbiotic archaea that we know of?
Methanotrophs, probably?
That sounds like a transformer. I don't know what you just said.
From ScienceSortOf.com, you're listening to Science Sort of.
Hello and welcome to Science Sort of. You're listening to episode 323. Our theme this week is harnessing the power of the great old ones. And joining me is a great old one. His name's Ben Tippett. Oh, I'm your host, Ryan Held. Ben, are you here to join me to talk about things that are science, things that are sort of science, and things that wish they were science?
Yeah, also my hair is turning white.
I mean, my hair's been going white since high school. So the worst thing for me is that now my chin, I have like the Ra's al Ghul beard now, Tim, with like the two white stripes going down from the lines, the corners of my mouth. Do you know what I mean?
Well, I look like Mr. Fantastic with the white in my hair.
You are pretty fantastic. I think. How stretchy are you?
Not very.
I always saw you as more of a Ben Grimm type.
Yeah, we have the same name.
Strong and melancholic. Well, we are joined by a guest this time, Ben, and allow me to introduce Kathryn Cogert. Hi, Kathryn.
Oh, hey, guys. How are you doing today?
We're doing well.
It's my favorite podcaster. Hi, Kathryn.
So,
no, it's my favorite podcaster. It's Ben. Hi, Ben.
Hi.
Stop complimenting each other so I can introduce you properly. Kathryn is a doctoral student at the University of Washington and is working on her Ph.D. in environmental engineering, as well as being the co-host of Encyclopedia Brunch, which is the show Tim Dobbs does. That's actually kind of hard to say, Tim Dobbs does.
Yeah.
It's good that wasn't the name of the podcast.
Yeah, thank God. I really had to push back on that. He really wanted that to be the name. It doesn't have brand appeal, man.
Well, thank you so much for joining us, Kathryn.
Thank you so much for having me. It's such a pleasure to be here.
This feels long overdue.
Oh, I'm so excited to be here. I hope I can live up to the hype, you know what I mean?
I think people will be delighted by you all the way through. So, you sent us sort of an introductory email to talk about your work, but in general, I said you were getting a PhD in environmental engineering, but what kind of scientist do you tell people that you are?
Let's see. I guess it depends on the exact circumstances. So I'll tell you guys that I do research on wastewater treatment, which means poop. I study poop.
Yeah, same. I also study poop. Ben, what kind of poop do you study?
Gross, you guys.
So much to learn from poop.
There's a lot of data in that poop.
That's what I told my thesis supervisor.
You mean your feces supervisor?
That's what he said.
Yeah, so I study poop, and specifically I look at, if you want the full rundown, when people, when you're at a party and people are like, oh, what do you do? What do you do? And you're like, what I do is, it's so many layers on layers because everybody's so specialized in this world. So I tell people, when they really push me, I say, I do research on energy efficiency and nitrogen removal of wastewater treatment.
Okay, good. So is that, I guess I wouldn't have thought that was a branch of environmental engineering, but I also don't know what else it would be. So is all wastewater treatment an environmental engineering problem? I guess so. That makes sense.
Yeah. I think if you really want to break it down, I think it's a cooperation between chemical engineering, which is kind of a jack of all trades situation. There's a lot of mechanical engineering. It's extremely interdisciplinary. I would say it's pretty firmly in engineering.
That's cool. Okay, so what's the problem with wastewater? Why do we have to treat it?
Okay, so
what is wastewater?
Wastewater is a pretty broad term. It can mean any water that we as humans don't want anymore. We've used the water. As soon as you're like, I don't really want that water anymore, it becomes wastewater. And that can be because there's pollutants in it, like specifically nitrogen or a bunch of organic carbon stuff or phosphorus or for any number of reasons.
And why are these things considered pollutants? Because, I think I hear nitrogen, I hear carbon, I hear phosphorus. I think those are the things we also talk about in like soil sciences that are necessary for plants.
Yes. Yeah. Okay. So you guys like the outdoors, right? Sometimes you go walking in the parks, in just by lakes, by rivers. You ever see like a pile of standing water and there's like a bunch of little green, they kind of look like leaves on the top of it. And like the whole surface of the water is covered with that.
You mean the algae or the lily pads?
The algae, the teeny tiny ones. Yeah.
Yeah. The kind that make you stinky if you like throw your friend in it.
Yeah. So that's a phenomenon called eutrophication when it happens too much. You get these they're called algal blooms. They're big blooms of this algae that accumulates because plants eat nitrogen and phosphorus. Algae are plants. If we bump nitrogen and phosphorus and carbon, like organic carbon, into bodies of water, the algae are going to go totally nuts, eat it all, completely overpopulate the pond, and then it gets all gross and stinky.
So what are humans doing that are producing wastewater? I guess is
Well, pooping.
Yeah, so is it just toilets and are we talking like a residential or a consumer level problem, or are we talking like industrial manufacturing, factory farming, or all of the above?
All of the above. Absolutely all of the above. It's really hard, though, to control factory farming style pollution because it's something called a non-point source pollution, in that it happens like we're leaving a bunch of, for example, chicken poo just out, and then it rains. And the water takes nitrogen and phosphorus that's in that chicken poo, and then it all sort of washes down in a really unorganized way into a body of water. And that's really, really hard to control, right? Because we can't control the rain. We can't control how that water channels. It's super difficult. So what we can control is water that's in pipes, water that you flush down into your pipes, and that also has a ton of nitrogen and phosphorus. There's actually a really interesting case study right here. So I'm in Seattle, Washington, and Seattle, Washington is partially around a lake called Lake Washington. And in the 70s, it basically looked like that pond that we were talking about earlier with a bunch of algae on top of it. You guys remember?
Yes.
Gross.
Yeah. The entire lake basically looked like that. It was so gnarly. And so a bunch of really smart environmental engineers from my alma mater got together, and they realized that what was happening is wastewater treatment plants, which is the place where we collect all the water you flush down your toilet. Those plants were just dumping basically just kind of semi-treated water. They were getting the poop out of it. They were getting most of the pee out of it. And then they were just dumping it into the lake, right? And so you can do that, but there's still a lot of nitrogen and phosphorus left over. And of course, all of these like 6 or 7 plants together were dumping tons of nitrogen and phosphorus into this lake. So of course we saw a huge algal bloom. So what they did is they increased the regulations. They did a bunch of exciting policy work that is completely out of my realm of expertise because politics are really hard. And they increased the regulations. So they said, hey, wastewater treatment plants, you need to make sure that your nitrogen levels when you discharge your water are below this amount. And that, like, within 2 years, the Lake Washington looked completely different. And today it's this gorgeous blue lake that people are kayaking and boating in, and it's amazing.
So, but why are these algal blooms something we want to prevent or not have happen?
Well, they're very ugly, for one thing. So that's the first reason. But for Mr. Moneybags, who's like, well, I don't care if the environment is ugly as long as my bottom line, you know, you can imagine like a Scrooge McDuck type character or something, you know, some sort of evil capitalist.
Mr. Burns?
Yeah. How do we convince Mr. Burns to care about the three-headed fish in that Simpsons lake? So
wasn't it Blinky? Wasn't that what they named the fish?
Yeah.
Yeah. So how do we convince Mr. Burns? And really, so it ruins real estate properties. So we lose, nationally, we lose something like, I can't remember the exact number. It's like 10 million or like 1 billion or something dollars per year because of eutrophication. So that's really bad. So it's a huge economic impact. Furthermore, it completely devastates aquatic communities, right? So you have a bunch of algae. And so these algae, they eat nitrogen and phosphorus. They also eat oxygen. So they deplete all of your oxygen. And then you have this really low oxygen environment. But fish need oxygen to breathe. So then the fish die. So that's really sad. And then you don't have fishing. You don't have, I mean, obviously that's a huge impact on the food web there and so on. Does that make sense?
These are like the dead zones in the ocean.
Exactly.
Right.
Thank you, Ben. Yes, that's exactly it. Yeah, we call them oxygen minimum zones or oxygen depleted zones or dead zones, which I think is a show on Fox, or it was.
I think it was USA.
Cool.
USA. Okay, thank you.
Don't know why I remember that. Never watched the show. I might be wrong.
It's good marketing.
Yeah, so, you know, we've I feel like I most often hear about this sort of problem when we get like big runoff into the Gulf of Mexico and you see this like wedge of algae blooming at the mouth of the Mississippi and creating these really big oxygen minimum zones. But it sounds like you're working on maybe slightly smaller scales, or what's sort of the scale of the problem that you're trying to tackle, or your field is trying to tackle?
Yeah, that's a great question. I don't think that wastewater treatment can fix oxygen minimum zones, unfortunately. And it's just because most of those oxygen minimum zones in marine environments specifically are because of the non-point source dilution, right? The chicken poo and then the rain, and then it washes into a river that washes down into the Mississippi that washes into the Gulf of Mexico, right? So really we can fix things like Lake Washington, though, which has been a huge impact and boon for my hometown here in Seattle. So wastewater treatment plants and improving nitrogen removal wastewater treatment plants can have a huge impact, though it can't fix oxygen minimum zones because that's too much fertilizer we're using in our agriculture.
Right, yeah, because fertilizer has a lot of nitrogen in it because that's an essential nutrient that plants can sometimes struggle to get depending on what the soil environment is like if you don't have nitrogen-fixing bacteria and whatnot. So what you said that you didn't understand the policies, the political side of what went into forcing these plants to. It's weird that it's the word plant and we're talking about algae, but we're talking about plants in an industrial sense.
Yeah, maybe we should switch to
facilities, these industrial facilities dumping the water. Yeah, obviously you don't need to walk us through the politics, but what changed about the science of what they were doing or the engineering of what they were doing?
Yeah, I think sort of extensive measuring and just monitoring of systems and like looking at the outlets every inlet into Lake Washington, for example, and measuring, okay, what's the nitrogen concentration in this stream, in this stream, in this stream, in this stream, and realizing that like, oh, it's mostly coming from wastewater treatment plants. That's totally our bad.
Oh.
And so what's the process? You said that the wastewater treatment plants back when the lake was in bad shape were essentially just filtering out, it sounds like they were just filtering out solid particulates and then just sort of dumping the water from there.
Yeah, I mean, I'm sure if you said that to one of the operators of those plants, they'd be like, we do more than that. We did more than that back in the 70s or whatever.
They got some of the pee out, didn't you hear?
The pee got out too.
But like, so do you know what they were doing after the policies changed, that they were able to do a better job of keeping the nitrogen from getting out into the ecosystem?
Oh, yeah. They implemented nitrogen removal systems into their wastewater treatment plants, which is pretty energy intensive. So that's why there was a lot of pushback. Like it was going to be very expensive for the plants to do. So that's why there has to be a lot of negotiation, especially in engineering disciplines of commonly used or required municipalities of like, well, we kind of need a nice lake, but it's going to be really expensive for taxpayers to pay for this nice lake. So that's the push and pull there. And I can't really speak to that. But what I can speak to is how nitrogen removal and wastewater treatment works.
That's what I want to hear.
Fabulous.
Yeah.
And so what happens? So I guess I kind of need to get into some science here. Are you guys up for that?
Sort of, but sure, let's try.
All right. So let me give you a rundown of what the nitrogen cycle is like.
Oh, I'm so excited. Are you excited, Ben?
Yeah, I love cycling.
All right, hang with me, boys, and stop me if anything is confusing, because I'm going to try to go as slow as I can. Okay, so nitrogen comes into a wastewater treatment plant. It's a little nitrogen atom, and it's like, awesome. And it comes in as ammonium with the chemical compound formula NH3, or NH4 in the case of ammonium. And you can think of it, it has no oxygen on it. And so what happens in the first step is we add a bunch of oxygen to it. And we do that with these really, really expensive aeration pumps that cost a lot of energy. And that's why it's so expensive. So we add a bunch of oxygen to it, and then it
So wait, you said
oxidized.
aeration pump? So that literally is just a pump that's adding air?
Just air, yeah.
Okay.
And I mean, wastewater treatment, it's so low tech that just even adding a pump to add in air is really expensive by their standards.
Wow.
Oh, but it's a standards thing. Because I was like, okay, so it's like an aquarium.
Yeah,
also,
it's like a really big aquarium pump.
You mentioned that it's really energy intensive by their standards, but I was also thinking in terms of like how the irony, you know, the sort of monkey's paw of I wish we had a clean lake, and the monkey's paw curls its finger and it's like, fine, we will do a better job of cleaning the wastewater, but we will need more power. And then the coal factory nearby starts pumping out more pollution into the atmosphere, and it's just like, oh no.
Oh. Yes, no, exactly. So the monkey's paw is curled. It's a beautiful analogy. I love it so much.
All right, but we sidetracked a little bit. So just the simple act of pumping air into the water does something to the ammonium.
Yeah. So a chemical reaction, well, not a chemical reaction, a biological reaction occurs. So an organism that we are just going to call ammonium oxidizing bacteria, it's sort of a group of organisms that we lump in together, and we call them ammonium oxidizing bacteria, also known as AOB. They take that ammonium and they take the oxygen and they oxidize it part of the way to nitrite, which has the chemical formula NO2. So that ammonium, it lost its hydrogen and now it has oxygen, and now it's a little bit more oxygenated. Make sense?
Yes.
Okay.
Yes.
And then this step's so a little silly. So then we have a second organism that's called nitrite oxidizing bacteria, or NOB. And then it takes that nitrite, that NO2, and it adds a little bit more oxygen. And it takes that and it goes to NO2, and it converts that NO2 to NO3. Make sense?
Yes.
Sure.
Yes. So those two steps together we refer to as nitrification. So it's two organisms doing two steps that completely oxidize our nitrogen species from ammonium to nitrite. But it matters that there's two steps, so that's why I'm making a big deal of it.
And when you say completely oxidizing it, you mean now the nitrogen can hold no more oxygen?
Yes. Yeah, it has 3 oxygen atoms. It's full up of oxygen. It's ready to go. It has a ton of energy for the next step, which happens in an anaerobic environment. Now, anaerobic means that there's no oxygen. So we've turned off our aeration pumps. There's no more oxygen being fed in. We have this like pool in the wastewater treatment plant. You might think of it, it's like, I don't know, maybe like a third of a football field big, this pool. And it's completely anaerobic in there.
33 yards.
Yeah, no, I know football.
Or 33.333 yards repeating indefinitely.
But it also has a width, Ryan.
I don't know I legitimately have no idea how wide a football field is. I just wanted to make my 100 yards joke. That's all.
Joke achieved.
Well, we'll let the listener be the judge.
Sorry, I'm not a good sports person.
Oh yeah, if this is a one consistency amongst the vast majority of our hosts and guests, it is our high level of sportsmanship. We're real sporters over here at Science Sort of.
Oh, great. I mean, if you ever want to talk baseball. But that's another issue. Let's talk about nitrification and denitrification. So we have this anoxic pool or anaerobic pool. Anoxic, anaerobic, they mean the same thing basically for our purposes. And then we have a bunch of nitrate. And then we have a third class of organism we're talking about. And they're called denitrifiers because they perform a process aptly named denitrification. So what they do is they take nitrate and a bunch of the organic carbon that's just sort of swimming around, because when you pee and you poo, there's a lot of organic carbon in there. So they take organic carbon and they take nitrate and they anaerobically reduce the nitrate to denitrogen gas, which is 70% of our air that we're breathing. So once it's nitrogen gas, it's no longer a pollutant. It's completely inert. That makes sense?
Yeah, I mean, because nitrogen gas, N2, is the majority of our atmosphere.
Yes. Yeah. So once the denitrifiers get their hand on that nitrate, we're kind of home free. As long as there's enough organic carbon for the denitrifiers to do their dark works.
And so essentially the issue we have here is there's no like naturally occurring bacteria that can take ammonium and turn it straight into nitrogen gas, so we have to go through these steps. Or
is there, Ryan?
I don't know. I'm learning so much.
Yeah, I guess that's the fun twist at the beginning of the third act of this story.
Because I know a little bit about these chemical reactions just because they have an effect on, like, nitrogen fixation is part of the process that affects the stable isotope geochemistry that I'm concerned with when I look at certain kinds of samples. And some of those chemical reactions are pretty similar, but it's essentially the nitrogen fixation that's happening in the soil with the nitrogen-fixing bacteria is bacteria that have evolved to take that atmospheric nitrogen, N2, and convert it back into ammonia, NH3, for plants to use. Which is exactly
Beautiful cycle continues.
which is exactly what you were saying, because if it stayed as the ammonia when it went back into the water pond, then it would be bioavailable to the algae, and that's what causes the algae bloom.
Exactly. Yeah, you're getting it.
Ben, are you following?
Yeah. Yeah, because I was taking notes.
Oh, were you?
Yeah.
Brag much?
Well, I mean, for a humble country physicist like me, there's a lot of nitro words here.
Yeah.
So yeah, we're good. There are 3 steps. The first step, the thingies take your NH3 or 4 or whatever and pull all the hydrogen off and slap 2 oxygens on there. And then in the next step, another dude comes in. I guess it's a dude. And adds another oxygen, and then you have to put it in a place with no oxygen, and the third type of bacteria pulls all the oxygen off, and then you have nitrogen gas, which doesn't do anything.
Yeah. And so ammonium oxidizing bacteria oxidize ammonium to nitrite. Nitrite oxidizing bacteria oxidize nitrite to nitrate. And denitrifiers, unfortunately, they're not nitrate reducing bacteria. Wouldn't that be convenient? Denitrifiers take nitrate and they reduce that to denitrogen gas. Yeah.
Okay, so I think that's a great rundown of sort of the problem that we're trying to solve and the way that we currently solve it. I think, as Kathryn, you hinted to a little bit in our next segment with you, we might be getting into a little bit of the cutting edge of fixing this problem even more better.
Yeah, dude, let's cut that edge.
Well, slow down. I think first things first. I think we're all a little thirsty, and we should probably take care of that biological need first. Thirst, and then we'll come back and talk more about the science. So
you need to give the bacteria something to do.
We're gonna walk on over to Ben's humble country drink nook and have a drink.
Visit my nook.
Next on Next Nooks. It would not be an episode of Science Sort of if we didn't also talk about what we are drinking. It's quite a bit earlier on the West Coast than here in the East, so I will ask Ben first.
Hello. Yeah, I'm a sleepy fella today, so I just brewed myself another cup of tea. It is black wild cherry tea from tdesire.com. Get all your teas online from tdesire.com.
Hey, wait, you can't hijack this segment for an ad.
Oh, should I talk to tdesire.com?
You shouldn't.
tdesire.com just canceled my favorite Irish breakfast tea, and they don't sell the Irish breakfast tea anymore, so I have to drink other weird tea from them, but it's okay.
Come on, tdesign.com.
What do you like so much about Irish breakfast tea?
Irish breakfast tea tastes perfect. Except if it's this like malted ball stuff. Few people make loose leaf Irish breakfast tea that tastes the way I want it to taste, which is to say good. Lots of people make it so it tastes bad, and I don't know why they do it, but it's getting more and more popular in terms of the loose leaf tea sellers like tdesire.com. And so I don't know why they're carrying it instead of the good stuff, but it means that I can't find the good stuff anymore.
And so you said, what are you drinking instead?
Wild cherry black tea.
Cherry. I'm looking at tdesire.com right again. I don't know why we've decided to turn this segment into an ad. They have a Canadian breakfast tea.
Well, listen, there's lots of different breakfast teas out there. I want specifically Irish breakfast tea. That's the only one that tastes good.
Okay, so can
All the other ones taste bad.
Now, with new Strawberry Moon, with our great strawberry tea, save 50%.
All right, so let's put out a call to our listeners. If you have a good loose leaf Irish breakfast tea source, let Ben know.
Yeah, on Twitter.
I did see you posting about this on Twitter, your upsetedness.
I complain a lot on Twitter about my tea.
Who else would listen, you know?
Bethany's heard enough.
Twitter is the internet equivalent of opening your window and shouting. It's great.
Yeah. It's kind of like being one of the butcher, the baker, the candlestick maker in the in the Beauty and the Beast.
You know, she's really mean to them in that song. I've been thinking about this a lot lately. And by lately, I mean the past couple of days. Like, she's really kind of snooty and cruel to this simple country town that's just trying to get by. There are wolves, there are giant monsters in castles. Like, it doesn't sound like an easy place to live. And she's just like, this place sucks and I'm too good for it.
Well, they're all illiterate, and that pisses her off.
But she could teach them to read. Start a literacy program.
Tried to teach
Belle?
a candlestick maker to read.
I think they're also really crappy to her for reading.
Yeah.
And she knows that's bull crap. She knows that.
Fair enough. I just, I think I don't think she's blameless. That's all I'm going to say.
Yeah, I mean, I think it's really hard to remember to be kind to our fellow man,
I think we're learning that lesson every day.
True.
Kathryn, what are you having?
Oh, hey, so you outed me that it's quite early here, so I'm going to sound like a real alcoholic, but... Guys, what are you drinking? How am I not going to have a beer? I'm having an Olympia beer because I'm here in Seattle, and beer actually makes a lot of wastewater that needs to be treated, so it felt appropriate.
Excellent. And it's Olympia. It's not like you're having some high-gravity, triple-hopped, 9.5%,
Oh, it's as close as you can get to water. It's owned by PBR.
So do you actually like Olympia, or are you just repping Seattle?
I actually do like Olympia. I mean, it is the same beer as PBR or Pabst Blue Ribbon. Absolutely it is. But I mean, I like crappy beers, and I make no bones about that. I'm fine with that.
I know some people, they prefer a crappy beer. That's their modus operandi.
If you like a La Croix, you like a light beer.
I don't like LaCroix. I can't say
together.
Because LaCroix this joke is not original to me, I don't think, but I say it so often that it feels ingrained at this point. And it's like LaCroix is like if water remembered the concept of fruit once, and then that's
Oh, it's like what's it called? Homeopathy pop.
It is like homeopathy soda.
What is homeopathy soda?
Well, homeopathy is that idea that like water has a memory, and so if you put
this garbage, right.
so like if you're having trouble sleep, and it's also this idea that like cures like, so if you're having trouble sleeping, what you need is a homeopathic dose of caffeine. So they put a caffeine molecule in a glass of water, shake it up, dilute it by taking like a few drops out of that and putting that in new water, shaking it up again, diluting that again. So by the time you've run through the dilution sequence that the homeopathic people claim that the medicine, the chemical caffeine has gone through, it's a statistical impossibility that there's any caffeine left in the water, but they claim that the water will then help you be able to sleep because the water remembers the caffeine molecule, and then the caffeine is actually the memory of caffeine will help you sleep.
Now that is some science sort of right there.
I mean, sort of feels like a strong endorsement relative to how bonkers that idea is, but speaking of caffeine, which I guess Ben already was, but I'm going to speak of it again. I'm also having some caffeine. I'm having some coffee from Perky Perky, which is a coffee roaster in Austin, Texas that my sister got me for my birthday, and this is their Wakey Wakey Costa Rican light roast. And it was pre-ground, so I can't put a pre-ground coffee in my espresso machine without breaking it, so instead I made some cold brew, and since it's hot anyway, that worked out great. And I'm drinking it, and it's real good. And you guys know light roast has more caffeine than dark roast, right?
Why?
That's weird.
Do you guys not know this?
No. It's the roast comes from the caffeine comes from the black parts of the bean.
Well, the caffeine comes from the bean, but it's a molecule, and when it's exposed to too much heat, it breaks down just like anything else would. So the longer the bean spends in the roaster, the more heat it's exposed to, the more of the caffeine that's actually chemically broken down. So the less time it spends getting roasted, the more caffeine is retained by the bean.
Whoa.
Yeah.
Okay, here's a question. So I've been getting really into the Starbucks app lately because of current events and the way that we can get our coffee.
And also, you just have to be as Seattle as possible all the time.
Oh,
it is
God. Seattle. No, true Seattle. Real Seattleites know that we never go to Starbucks, and we think less of each other for going to Starbucks.
And yet here you are.
Whoa.
And yet here I am. I mean, I drink Olympia PBR-owned beer. I'm not a snob. But so one of the options in the app is to get the blonde espresso. So does that have more caffeine? Because they put it in the same category as decaf.
Starbucks has always been very cagey. Also, I said that this was a birthday gift for my sister, right?
Yeah.
Thanks, Nicole. It's good. It's
Thanks, Nicole.
Yes.
legitimately
Well
very
done,
good.
Nicole.
Very good cold brew. I'm enjoying it a lot.
Nicole.
Nicole brew. That's good. I like that. So Starbucks has always been very, very cagey about like what their actual roast profiles are. So they tend to like use words that don't actually make sense from a roast. Like they have like a roast that's like, this is our robust roast. I'm like, okay, but that's not a helpful term. Like that doesn't mean anything in a roast profile. Like, so you're just trying.
Ryan, it's robust.
So it's like they're just trying to brand it, or they're just trying to obfuscate, or they're just trying to like, I don't know, make it more difficult for a person who actually cares about coffee to engage with their product. So my assumption, based on using the word blonde, they are saying that it is a lighter roast, but I have like pointedly asked this at Starbucks locations and they don't know, which is fine. Like I don't.
Yeah, 'cause that kid's 17, Ryan.
Yeah, no,
Nice to
I don't blame them.
Nice
but like,
to your service workers, your essential workers, Ryan.
I asked out of curiosity. I did my best not to be antagonistic. I still ordered and tipped, and everything was fine. The blonde roast does taste better to me, and I find that the vast majority of Starbucks blends taste over roasted for my palate. I barely go beyond a medium roast most of the time. Dark roasts are often way too dark, and too much of the roast comes through and not enough of the bean. So the fact that I like the blonde, if it's available to Starbucks, that's what I get, suggests to me that it is a lighter roast.
I see. But that's not Starbucks' cardinal sin. Starbucks' cardinal sin is they don't tell you what they serve on any of the menus. Instead, you just get to look at a nice big advertisement for whatever they're making that week or month.
Yeah.
And so you're supposed to psychically know about all the different drinks you can order there.
Yeah.
I don't know what to order because you don't list them. And then I point at one of the pictures and I say, can I have that one? And they say, no, we stopped selling that a month ago. Starbucks, you're supposed to write down what people can order somewhere.
I am so behind you on this, Ben. This is my biggest pet peeve too.
Come on.
Starbucks.
There was a coffee roaster in Nashville that had a Starbucks sort of, it was their version of a Starbucks blend and roast, and they called it Charbucks, and I always enjoyed it. Enjoyed the joke. Didn't enjoy the coffee. Too roasted for me.
Too dark?
Yep, too dark. I like a light roast.
All right, that's Ryan. He likes the light roast. Put it on his gravestone.
Well,
yeah.
Speaking of other things that get filtered, like coffee,
Like what?
water needs to get filtered too. Let's talk more about that.
You're drinking Texas coffee. Aren't you supposed to drink that like a cowboy?
Oh, like brewing a sock?
No. Listen, here's what cowboys do. They take the coffee grounds and they put them in the cup, and then they put the hot water in the cup, and then they wait a little bit, and all the grounds settle to the bottom, and then they drink it.
But
you
I
can
didn't
just use gravity to filter out all of the grounds, Ryan.
Well, I sort of
That's how cowboys do it in Texas. Are you too good for Texas?
I sort of
Did
did.
you forget the Alamo, Ryan?
I did. I forgot. Forgot the time that. Well, I'm not gonna. Let's not get into the Alamo right now, Ben. We're gonna lose listeners if I start talking about how I really feel about the Alamo. I mean, I sort of did that, Ben, because I did make this as cold brew. So I put a bunch of grounds in my French press and then poured just cold water over them and let it sit for like 12 to 24 hours, and then pressed the plunger on the French press and then strained it out that way. So I mean, similar.
French press.
Yeah.
I hear you talking about cowboys and French presses in the same sentence.
That doesn't compute for me.
Well, French press is stainless steel. Does that make it manlier?
It's not about manliness. French people are plenty manly. It's just cowboyiness.
Cowboyiness.
There's not a lot of French cowboys. I think that's what I'm coming up against.
Yeah, you have Spanish cowboys, vaqueros, and the American cowboys, the buckaroos. Two types of cowboys,
And
one type of coffee.
The men who are part cow, the monstrosities.
Oh, yeah.
Don't forget them.
That's right. Yeah. Our Minotaur is the Minotaur a cowboy?
Cowman.
No, that's a bull boy.
No, it's cowman.
Very manly.
So our theme this week was harnessing the power of the great old ones. I don't think we've really gotten into what that theme means. So Kathryn, what comes next? We covered the basics of wastewater management and sort of the basic science of how we try to get nitrogen out of the water. Where does your research come in?
Yeah, I think just to recap last time on Science Sort of.
If you're just tuning in now.
You gave us this fabulous cliffhanger that I absolutely loved, where you said, so this whole ammonium to nitrate thing, it's really energy intensive, and it's the only way to get to denitrogen gas, right? You have to go through this whole cycle of oxidizing the nitrogen all the way to nitrate, and then reducing it to denitrogen gas. And I'm sorry, just as a lexicon thing, in my field, we often refer to it as dinitrogen or denitrogen gas. I don't know if it's like a European thing. It's just what has been
just because it's
read
N2
into me at this point. Yes, because the chemical formula is N2. So if I say denitrogen or dinitrogen gas, I'm just talking about nitrogen gas that you're breathing right now as we're talking. But anyhow, so you gave us this fabulous cliffhanger where you're like, we have to go through this whole freaking rigmarole. And I was like, maybe there's a better way. Maybe there's a faster way. And this is where our friend Annamox comes in. And Annamox is what's it called? It's an acronym. Yeah, because it stands for anaerobic ammonium oxidation. So this is in contrast to, you remember I said, well, we need to add oxygen in to oxidize the ammonium. Annamox actually can do it without oxygen. What it actually does is it takes a little bit of ammonium and a little bit of nitrite, and it shortcuts the nitrogen cycle really quick. So it takes ammonium and nitrite and takes that directly to denitrogen gas. So you don't need nitrite anymore. No more nitrate, no more NO3. And so you need way less oxygen. So you can think of it, we put in oxygen to convert 100% of our ammonium to nitrite, and then 100% of our nitrite to nitrate. And this you only need to convert maybe about half of our ammonium to nitrite. And so we're only doing partial nitrification. So we're only doing that first step, and we're only doing it to half of our influent nitrogen. Does that make sense?
I think so. My question, though, is, so wait, where do these Annamox bacteria come from? Because I guess the bacteria being used in the previous steps, or in the previous method, you said, it's a class of bacteria. So presumably they're relatively common, they're easy to go out and get. Is this Annamox type of bacteria, is this a new discovery, or did we just not think about using it in this way? What's the backstory in the
Yeah,
of the
so
Annamox?
it was discovered in the 90s, which is it's a tiny baby of an organism as far as what we know about it. It's existed way, way beyond that. It was just kind of hard for us to catch and to figure out. We couldn't quite see it, because it was really hard. It's always existing with all of these other organisms, and it's really hard to isolate it as an individual cell and get it to grow like that. So it's really hard to have an Annamox isolate, we call it, where it's just Annamox in your culture. And so it was really hard for us to catch. So we kept missing it in the nitrogen cycle until someone's like, hey, this nitrogen balance, I'm trying to figure out where my ins are going, where my outs are going, and it doesn't quite add up. And then they found this old paper from the 70s where somebody had predicted this reaction. This ammonium plus nitrite goes directly to denitrogen gas, just purely based off it's thermodynamically favorable, so why not? Why couldn't an organism do it?
And where does the nitrate, the NO2, come from in this process? Oh, you said that was where you said you only have to convert half your ammonia.
Yeah,
is that what you meant there? Okay,
exactly.
Gotcha.
So we call it shortcut nitrogen removal. It's one thing that we call shortcut nitrogen removal when we use Annamox.
The science paper you shared has a very elegant figure kind of showing how the shortcut works.
Yeah, where it's just you can see this big blue nitrogen cycle. It's this huge circle, and then these two red lines that are just doink. We're just shortcutting it.
Yeah, so that paper is Sewage Treatment with Annamox, Cartel et al. 2010. So I'll include a link to that paper on the show notes to the website, and hopefully people will be able to access that and see this nice little figure that I think clarifies the process quite cleanly.
Get into it, guys.
Okay, so that's one relatively novel method for improving this process. Has it been implemented? Are people making it work?
People are using Annamox. There's over 100 treatment facilities that are using it at full scale. But I want to put an asterisk on that full scale, because the problem is that Annamox needs only nitrite, right? So it doesn't use nitrate. if you accidentally go too far in the nitrogen cycle and you accidentally have some NOB in your process now that are taking some of that nitrite and taking it to nitrate, then you have a competition going on, and it's NOB versus Annamox. And at mainstream conditions, we think of it, which is quite cold, and by cold, I mean like 10 degrees Celsius. Annamox is going to lose every time to NOB, every single time.
Huh. Okay, so Annamox isn't the toughest little bacterium out there on the playground.
Yeah, so we have this competition going on, right, between Annamox and NOB. And at mainstream conditions, NOB tends to win that because it's so cold. And we can try to, because NOB need oxygen and Annamox don't, we can try to control it at a really low dissolved oxygen, because ammonium oxidizing bacteria are able to grow faster at lower dissolved oxygens, just because of the way their growth kinetics, we call it. They're something called a K strategist, which means they grow really well when they don't have a lot of nutrients, whereas NOB are more of an R strategist, meaning they grow a little bit slower at low nutrient conditions and they grow faster at higher nutrient concentration.
Okay, that's weird, because R and K are also the letters used for different types of like vertebrate reproduction strategies. So
Really?
yeah,
Interesting.
like well, I guess not even just vertebrates, but animal reproduction strategies. So like a mosquito lays thousands of eggs and expects that most of them won't survive, but as long as a few do, that's fine. Whereas humans have, one baby at a time, and we put a lot of investment into that one baby. So.
Oh, yeah. We are K strategists and mosquitoes are R strategists.
Yep.
Because mosquitoes are using a ton of resources to make all those eggs. Whereas comparatively, on like a per baby basis or something, I don't know what you would normalize this to figure it out, but it's in bacteria and in microbiology, we think of it as like how many resources we're using. Whereas I think it sounds like, if I'm understanding you correctly, in reproduction biology, it's more like, well, how many babies do you have?
How much investment per baby?
How much investment per baby?
As an inverse relationship with how many babies. So the assumption is the more babies, the less investment. The fewer babies means more investment per baby.
Okay. Yeah. That makes
Then you have something like crocodiles that lay out these little eggs, and then the mom is still like, don't worry, little baby crocodiles, I'll help you carry around and stuff. So who knows?
See, it'd be so cool to find bacteria that act like that too. Anyway, we're sidetracking ourselves. Let's get focused on Annamox.
Let us.
All right. So this is the problem. And so Annamox works really, really well in higher temperature side stream conditions, which is only about 2% of your flow, but it ends up being like 20% of your total nitrogen loading in the plant. So these really high nitrogen concentration, high temperature streams. And that's where Annamox really thrives. And that's because AOB are really limiting us, because at these oxygen concentrations that it's required to select for AOB over NOB and Annamox over NOB, for those particular oxygen concentrations, you tend to reduce the efficiency of AOB. So AOB aren't quite able to keep up. They're not able to supply Annamox with quite enough nitrite. And so instead of like the 99% conversion to denitrogen gas that we'd like to see, you see like maybe 80%, 70%, in there.
Okay.
And so this is where we introduce another new friend that was also discovered in the 90s. And this is called ammonium oxidizing Archaea.
Are you happy, Ben?
Yes, I love Archaea. Tell us about Archaea there.
Well, what are Archaea? Let's define Archaea first, and then get into this specific type of Archaea.
Yeah, actually, I wonder. So we have an Archaea fan in the audience. Ben, could you help me out with what an Archaea is? Because my perspective on Archaea is, well, they're a little factory that do the thing.
Well, I mean, okay, so tree of lifetime. Most of you remember that there are bacteria, which are single-celled organisms. They're not the only single-celled organisms, though, right? Like amoebas aren't bacteria, right?
Right.
Okay, so bacteria
yeah, prokaryotes and eukaryotes.
Yeah, so you might be familiar with eukaryotes. So anything multicellular is a eukaryote. So animals, trees, ciliates, I don't know.
And there are single-celled eukaryotes too. But you're right, multicellular life is eukaryotic.
Yeah, so these are branches on the tree of life. They come from, they split off earlier and earlier in the evolution. Bacteria went one way and eukaryotes went another way. So there's this third tree of life, Archaea, which must have split off a long time ago as well. Anyway, so that's what we're talking about. They're single-celled organisms that aren't bacteria. and they're really well. That branch of the tree of life is really, really, really old. So
And they tend to be extremophiles, at least in the modern world. So they tend to live in very extreme environments that other things couldn't survive in. So they're some tough little buggers.
yeah,
Right?
yeah.
I mean, if I'm saying something, oh, here we go.
I got the actually person, but that was the common dogma about Archaea for a really long time because we kept finding them in these really extreme environments. I mean,
well, redogma us.
And then we started finding these ammonium oxidizing Archaea, and they're like the most common prokaryote in the ocean. And so it's hard to say like, well, all of the ocean is an extreme condition. So there's something like that. Don't quote me on that. I don't have my citations in front of me, but they're extremely common in the ocean. The issue is that they really thrive at low oxygen and low ammonium conditions. And also some of them thrive at extremely low temperatures too. And so you might see how like, maybe they're a better alternative to AOB. Maybe we want to use AOA instead of AOB to supply Annamox with the nitrite that they need to remove nitrogen. Are you boys with me?
Right. Okay.
50% of the ammonia that needs to be converted to nitrate first could be done by the Archaea, and that way you're not worried about the competition between the Annamox and the other bacteria.
Yes, except it's converted to nitrite. Sorry.
Nitrite.
I can't control that these words are one letter apart. It's the stupidest thing.
I remember learning all of these chemical conventions when I was taking chemistry in college. I just don't use them often enough to keep them totally straight in my head.
Oh,
these days.
yeah. No, absolutely. I swear. We do it in my work all the time. People mess it up all the time. And we just correct each other because with compassion, I guess. Because and whenever somebody gives a presentation, and I might have done it on this podcast already, I say nitrite. So it's extremely obvious.
That's good. No, I appreciate being corrected. Okay, so
Okay.
sort of what
Can I-
what I yeah.
All right.
go ahead.
Can we review this? Because like I'm a stupid humble country physicist. All these as soon as you stop talking about atoms, I get kind of lost. I realize it's not quite organic chemistry, but I'm like, okay, so nitrates and nitrates are anyway. So we have a 4-step process that you introduced at the start of the show. So it's like, I don't know, pizza.
Yeah.
Your NH3 or NH4, let's call that like flour. So you got that, and we want to turn it into pizzas at somebody's home, which is N2.
Uh-huh.
So the step process, first, you got your, what is it, AOB, right? And those are the guys that take the pizza flour and turn it into pizza dough.
Sure.
And then the nitrite NOB, oxygenating bacteria, turn that pizza dough into, they put the toppings on it and bake it. And then you put it in an anaerobic environment, and that's like the pizza delivery person who brings it to your house. And then you got N2, a 4-step process.
Thank you for breaking this down in terms of the Domino Pizza tracker.
Thank you. Yeah, I know. It's all I understand anymore now that since the plague hit. Okay, so what you're saying is Annamox cuts out kind of the first step. It goes like, well, if we take some of that pizza flour and turn half of it into pizza dough, then our Annamox bacteria takes those two and turn it directly into pizza without those intermediate steps.
Yeah, through, I guess, magic in this analogy, but yeah.
Yeah, through magic. But the problem is that the Domino's pizza people start fighting with it and can make pizza in normal conditions. They can take the pizza dough and they'll start making pizza out of it. Yeah. And so you can't quite. There's two processes. I mean, they're bacteria, so you can't stop them from doing it, and so it's not very efficient. So the goal here is, instead of taking Domino's pizza people to do the first step, taking it from flour to pizza dough, you're replacing that first step with these Archaea. Is that it?
Yes. Maybe what we're doing is we're sucking all of the oxygen of the room and hiring pizza bakers who can work at lower oxygen conditions.
Sounds like a real human rights abuse.
Yeah, it's messed up.
You're sucking all the oxygen out so nobody can come to work, and then you're hiring pizza robots to come and make it into flour instead of relying on the helpful labor of Domino's pizza employees who will then immediately try to turn it into pizza.
Well, I feel like a monster now, but yeah.
But in this analogy, the robots evolved first. So
Yeah, that's right.
So we're bringing in like these really old robots.
You know, it's really, and honestly, if we get back to the Tree of Life thing, it's actually pretty unclear whether the Archaea are like, the robots are like sisters to us, or like they're our parents.
I guess what I was always told, at least the thought was, before we really started understanding more about Archaea, was the assumption of their ancientness came from the fact that because we didn't find them, we found them in these extreme environments. Maybe the assumption was sort of like, well, that must have been what the environment of Earth was like when they evolved. So they're just persisting in these environments that are similar to the extreme conditions of early Earth, and they've been outcompeted or excluded in some of the easier to live in environments by the tougher, more ferocious, more modern bacteria. But again, that's that's what I sort of remember being taught, that is probably based on a lot of assumptions, and the fact that we're finding them in a lot of other places like the ocean suggests that maybe that's not true.
Yeah, so you can think of these are the ancient old robots that we're harnessing the power of.
I love it.
Cool.
The Celestials in the Marvel cosmology.
Yeah. Yeah. And one really, really neato bonito thing about this is that Annamox, and the reason why we're very confident that this will work in some capacity in wastewater treatment, because I don't know, I think it's a very reasonable thing to be like, all right, so you have organism A and organism B and you want to sort of crunch them together. Why do you think that these robots and these pizza delivery men will work well together? And women, pizza delivery men and women, and non-gendered binary people.
Pizza delivery people, pizza people,
These
pizza apple.
Yeah. And the reason we think that these robots and these pizza folk will work well together is because they're already doing it in the oxygen minimum zones of our oceans together.
Okay.
Yeah. So what we're trying to do is mimic what's already happening in these oxygen minimum zones of the oceans, which, if you guys remember right to the first, 10 minutes of our show here today, we were talking about there's a lot of these oxygen depleted zones that are increasing in size. And because they're increasing in size, there's been a lot of study around these increasing in size oxygen depleted zones. And what we find is actually the solution to reduce nitrogen pollution that may be causing some of that.
So that was adorable.
So the solution to pollution is ancient robots from the dawn of time.
It's not as catchy as solution.
Single-celled ancient robots.
Yeah.
So what exactly is the project that you're involved with for your PhD work that is kind of wrapped up in this whole system?
That's the whole thing.
Okay.
Yeah.
Cool.
Yeah. So I've spent the past 4.5 years trying to get these two freaking organisms to work together in a freshwater environment, right? Because we don't have salt water in our toilets, and we only know of Annamox and Ammonium oxidizing Archaea working together in oceans. And so I'm trying to get them to work not only in freshwater environments, but also in biofilms. So I completely skipped over this fact, but another extremely cool thing about Annamox is that they grow in these spherical biofilms that we call granules. And so what you have is you have this bulk fluid and you have these granules. They're kind of like beads and they're being aerated. I'm sure Ben or Ryan, either one of you could think of a really good metaphor for what this might look like.
Of beads being aerated?
Yeah, is that good enough, or can you guys think of something
like
cool?
the lottery machine with the ping pong balls all swirling around in the air?
Yes, totally.
Okay.
Totally.
There,
so,
that's my analogy.
It's beautiful. So ping pong balls, they have a shell, right? And that shell is where the oxygen is penetrating. And so then you have, in traditional Annamox, it's AOB that are living there. And in my Annamox, what I was hoping to do is swap out that AOB for AOA. And so that's where all of the oxygen gets consumed right in the shell of the ping pong ball. And inside, all of the oxygen's been consumed. So that's the perfect environment for Annamox to live together. So why am I going on and on and on about this is because then instead of this huge 33-yard a third of a football length and then another tank for nitrification and denitrification, we smush them together in one single teeny tiny reactor that's like, I don't know, it's like a 70% size reduction or something like that. I don't remember the number off the top of my head. And that's a really big deal, especially when we're trying to treat wastewater in like really crowded urban environments and we're really limited on floor space that we have to use.
That's awesome. That's really cool.
I think good.
I think this all came around nicely, and I guess you'll have to come and give us an update when you've solved the whole thing.
Yeah, no probs. Let's do it.
All right. Well, if anyone out there listening has an update they want to give to us, they can do that by sending it in on the contact page at scienceorb.com. And if you do that, you might get featured in our final segment of the show, the Paleo Pow. PaleoPOWs is the final segment of the show where we take in some feedback from the listeners, and it's going to be a lot of fun. But first, before we do that, Kathryn, you have a show to plug.
Oh, yeah. So please check out my and Tim's other PaleoPOW. Also a paleo, or I don't know that I can call myself a PaleoPOW. Let me try.
You're honorary for this episode at the very least.
Oh, Dolly. So PaleoPal, Tim Dobbs, is my podcast co-host of, 6 years now? 7 years now? Yeah, 6 years now. And we have been producing Encyclopedia Brunch together. And we have almost 300 episodes at this point. And there's a very deep back catalog. We release fairly infrequently, but I think there's some good goofy content in there if you like goofing around. It's much less serious than Science Sort of.
And you sort of take an encyclopedia-type topic and talk about it.
Yeah.
So it's very random in its subject matter, but each of the subjects you manage to find something about it that's interesting and talk about it in a way that's amusing to listen to, which is the whole point of a podcast.
Ryan, you're a better pitch man than I am. Thank you so much. Thank God you saved me.
Not a problem. Well, speaking of pitching podcasts, I'm going to do my PaleoPOW here at the beginning. And I want to give a special shout out to Joshua C., who posted about Science Sort of in a Facebook group called Wild Green Memes. And somebody asked what their favorite scientific podcast was. Bonus if it was ecology, biology, or zoology based. And Joshua chimed in and said Science Sort of is the best. A lot of biology, paleontology, and even astrophysics, Ben. Laid back and hilarious, just the right amount of wacky to balance the awesome science, and they talk about beer a lot. It's awesome. So thank you so much, Joshua. It's really nice when, we kind of get alerts about that sort of stuff when people tag our Facebook page, but it's really cool when people ask for podcast recommendations and we can actually see it happen in real time, in the wild. And I think most people who are coming into podcasting are looking for recommendations. So if you have people in your life who want podcasts and you want to recommend us, that's awesome. So thank you, Joshua, and thank you everyone else who recommends the show to friends and fam. Kathryn, I sent you an email.
Yeah. Shall I read it out loud for you?
Yeah, what do you got for us?
All right. This is from Gerrit. Thank you for writing in, Gerrit. Gerrit writes, "Hey, Paleo Pals. I was just listening to episode 319 and heard you guys discussing drinking water in spaceships being used for radiation shielding and being concerned about that prospect. As a real deal nuclear engineer, I felt I could chime in." Thank you, Gerrit. "The primary concern in space, as far as I know, is high energy neutrons and high energy ions. For both types of radiation, water is an excellent shield and is in fact commonly used in my line of work. When it comes to the activation, the term for when something becomes radioactive, the two things to keep in mind are the probability of this reaction happening, called the cross-section, and how long lived the radioactive thing you made is, i.e. the half-life. Water is nice because the two constituent atoms, hydrogen and oxygen, have a low probability of activation from basically all types of radiation, and when they do not become radioactive, they tend to decay quickly. Radioactive oxygen has a very short half-life and is commonly dealt with in water inside of nuclear reactors. The water is safe to be around minutes after the reactor has shut off, although please don't drink it, as it's very pure water that is very expensive and still has some radioactivity in it. Radioactive... I like that.
Very expensive water. Yeah.
Radioactive hydrogen, called tritium, will stay in the water much longer as it has a half-life of about 12.5 years. It is probably the least dangerous radioisotope, though, and very valuable as fusion fuel. Any prospective space colonists would gladly filter that liquid gold out of their shielding water. Tritium is neat because even when it decays, it becomes something valuable. The decay of tritium produces a high-energy electron called a beta particle, a neutrino, and helium-3, which is a special isotope of helium that is also useful for fusion and detecting neutrons. Helium-3 is the fusion fuel you often hear people joke about mining the moon for. So, rather than becoming a problem for space colonists, the radiation of outer space hitting their drinking water is actually probably a blessing. Thanks for the great show, and keep up the good work, Gerrit. P.S. I love the portion where you guys ripped into Musk. He needs to be taken down a couple notches. I also like that portion. Elon Musk sucks.
Yeah. I think we really need a Kryptonian disguised as a reporter to come and help us out with this Elon Musk problem.
That sounds cool. Okay.
What do you think, Ben?
Sure.
Does the physics check out?
So, on Earth, when we're trying to do nuclear fusion, usually what happens is you can make fusion happen, but the amount of energy it takes to make fusion happen exceeds the amount of energy that is released by fusion happening, which is why we don't have fusion happening powering our cities yet. Basically, the simplest way to talk about fusion happening is you want to start with a bunch of hydrogen atoms, and you want to smush them together until you get a helium atom. Helium has two neutrons.
Catherine, you gotta shmush.
Are you happy? Yeah.
You got an official Ben Tippett shmush.
Two neutrons and two. You get 2 neutrons and 2 protons all together. So the way it happens inside of the sun is something called the proton-proton chain. The proton-proton chain is really, 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 really inefficient. It's really inefficient because of the first step. You take 2 hydrogen atoms, which are just protons, and you smush them together to make deuterium, which is a proton and a neutron stuck together. Okay?
It's an isotope of hydrogen.
Yeah, it's an isotope of hydrogen. It's the isotope that you use to make heavy water, incidentally, which is where you might have heard of it. So deuterium is that step where you take 2 hydrogen and mush them together to make a deuterium. That step almost never happens. So you need these collisions to happen at a huge scale to get a few deuterium nuclei forming. It's just so rare. I think my favorite comparison is, in terms of a kilogram of material, the amount of heat released inside the core of the sun per kilogram is less than the amount of heat per kilogram that you get from a compost pile. Our bodies actually per kilogram release more heat through processes, biological processes, metabolic processes release more heat per kilogram than the core of the sun. And so one consequence of this is, if you want to harness nuclear fusion on Earth, you have to create plasma that's a temperature which exceeds the temperature in the core of the sun. It's bonkers. Anyway, so after that, you take these hydrogen, you smush them together, and you get helium-3. So that's 2 protons and 1 neutron. And then you combine those 2 to make a helium-4 together. Okay, so long story short, what Gerrit just told us about says that you can filter the byproducts of the shielding water. You can filter it out for essentially isotopes that are partway down the proton-proton chain so that you skip the most inefficient step. It's kind of like, instead of trying to make pizza from scratch using buying a pre-frozen pizza where you just have to take it and put it in the oven. It's all the difficult stuff's done for you. Fantastic.
But frozen pizza's never very good.
Well, it'll keep you warm.
Have either of you ever got to hold a bottle of heavy water?
No, have you?
Yeah, it's weird. It's like, to make an analogy, because I know Ben loves analogies, it's like if you were at the dentist and they were getting ready to take the x-rays and they were getting ready to put that smock on you, but you thought it was just like a normal fluffy, it's just going to be this nice little blanket, and then they put it on you and it's lead, and you're like, oh my gosh, it's so heavy and dense. That's what a bottle of heavy water is like. You're like, oh, look at this bottle of water. Then you pick it up and you're like, oh, it's like Mjolnir. Am I worthy to lift this bottle of water?
Yeah. Well, you should. Oh, yeah. And incidentally, there's an additional thing I want to add to Gerrit's point about the water from nuclear reactors. If you have really, 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 really pure water, you don't want to drink it because it will osmotically leach calcium from your bones and other minerals from your bones.
Yeah, that's so exactly what I was going to add.
It also does. I mean,
don't
drink really, really pure water.
Yeah. Not only is it very expensive, but it's also like reverse Gatorade.
It also doesn't taste very good. Like you might think that pure water would taste like pure water, but it is the other things that are dissolved in the water, the other minerals and chemicals that are in there at very minute concentrations that actually give water its flavor.
Fish butts, yeah.
Don't drink purified water. Well, hyper purified water. Don't drink homeopathic water. What water should people drink?
Well, you can drink homeopathic water because it's just water. It's completely.
Don't drink it for your paycheck more than anything else.
that is a good tip. Water tips from Kathryn and Ben, the new podcast coming to you.
Yeah.
Each week they review a different kind of water.
This is good.
This week, semi-heavy water that has 1 hydrogen and 1 deuterium.
You know,
fully heavy.
I like to drink my water from a tall glass rather than a short glass because I find it really filters down the throat better.
As long as the water doesn't have the memory of the glass that it was in.
Oh boy, yeah. Well, maybe you do because you want to be tall instead of like short and squat. That's how it works, right?
There's a statistical mechanics calculation that we make all like third-year students do where you show that in all likelihood, some of the air in your lungs was part of Julius Caesar's last breath. And similarly, you can show that some of the water in your body has been in and then you fill in the blanks, anything that's held water in the history of the Earth.
I usually see it like a dinosaur.
Yeah.
Or something.
So in that context, the water has been through everything with every property. So you don't need to buy the fancy homeopathic water because tap water has also been next to like an arsenic molecule or whatever the hell. Tap water remembers just as much as fancy, expensive homeopathic water. Treat your grandma with a nice glass of water.
So you're suggesting some sort of omni-water memory theory of pan-dimensional homeopathy?
If water remembers anything, then it remembers everything.
I think you two have a great spin-off show just talking about different kinds of water. But we have to end our episode this week by coming up with a thesis for one of our patron donors. And this week, our patron donor being featured for a thesis, he's completed the other requirements. All that remains is the BSso, which is the fake degree we give out, Kathryn. And that's Will Q, which is a great rap name, not his actual last name. But Will's actually a buddy of mine, so this is exciting. I'm eager to come up with something clever. So, Kathryn, I assume you're a frequent enough listener that you're familiar with this topic, but basically we kind of play around a little bit with some of the ideas that we talked about in this episode to come up with a bonkers, silly, outlandish thesis for Will.
Oh, fun. Okay, let's do it.
Will also works with dogs, so is there a way we can bring dogs into your research on wastewater treatment, Kathryn? That's kind of where
dog puns abound.
Can we come up with a new method for doing wastewater treatment that's acronym is like pupper? What do you think, Ben?
You have to call them canines if you're writing a paper about it.
Or canids if you're talking about all dogs.
How about Canid ammonium titration?
What about are there any Archaea? You know, we have a lot of symbiotic bacteria that live in our gut. Are there any symbiotic Archaea that we know of?
Methanotrophs, probably.
That sounds like a transformer. I don't know what you just said.
Transformers.
I am Methanotrof!
How about
Annamox sounds like a type of Pokemon, and it's been bugging me the whole time.
It does
and
sound
I
like
was
a type
being
of Pokemon.
professional this whole episode, but
No,
if you're
you
going to
weren't.
bring Transformers in.
Don't lie to the gentle listeners about your professionalism, Ben.
What about
So, wait, okay.
Canid we get...
So methanotroph means like a methane eater, right? Like a methane metabolizer.
I'm so sorry. I need to correct myself. It's methanogens. All methanogens are Archaea.
So what if we like found a methanogen because a dog had like bad farts and we realized it was like methanogens inside the dog's gut?
Oh yeah. So it's like Canid, we find some new methanogens in this dog's gut.
Yeah, I think you need to preface anything like this with like a short phrase in like, modern English. So you'd say something like, blame it on the dog, quote unquote, and then colon, everything's topical, canine, etc.
Blame it on the colon.
Blame it on the colon.
I don't know. I love the pun. I love the wordplay of Canid. We find. So here's what I wrote.
Okay.
Canid. We find some new methanogens. ? Novel discovery of methane-producing Archaea in the GI tract of Canis lupus familiaris.
Okay, that sounds good. What's the acronym spell out? Does it spell out an acronym?
We didn't end up going with the acronym. We just went with the wordplay pun of Canid. Can't we? Canid. Canid. We find some new. So I spelled it Canid. Canid. We find some new methanogens.
That's pretty good.
I think that's strong.
Colon, barking up the right tree.
Done.
I don't know. Is clapping okay on a podcast?
Yeah, if it's not, if there was ever a moment for it, though. All right. Sold in the room. Thank you so much, Will, for being a supporter of the show. We hope you enjoy your thesis. Will, if you want to get in touch with Kathryn to, let her know if she can use your newly discovered Archaea or not in her experiments, Kathryn, where would he do that? Where can we find you on the internet besides Encyclopedia Brunch?
Oh, y'all should just hit me up on Twitter. I'm at Kathryn Isabel. That's Kathryn. Isabel, Isabel. And I don't really tweet a lot about science. I mostly tweet about goofs.
Well, if people tweeted you after listening to this episode and asked about science, would you be willing to engage?
Fine. Yeah, let's hang and talk about science, Yeah. But,
excellent.
I probably won't start the conversation about science. Much more likely to start it about some annoying new feature PowerPoint has.
Well, that's a bigger part of the scientific endeavor than people realize.
PowerPoint's the worst.
Ben, what about you? What do you got going
on? Titanium Physicist is going to be, I don't know when it's going to release. This episode's going to release, do you know?
A couple weeks.
I don't know. Do you think the world will be worse? I've got an episode. Titanium Physicist.
Almost
going to come
certainly,
back
yes.
As soon as I don't feel like I'm interrupting what's it called? A funeral.
A movement.
Everything's getting worse. I keep waiting for things to get better so that I can be like, hey guys, things are starting to improve. Here's some physics, and it just doesn't happen.
I think we need diversions more than ever right now. I think that is a form of supporting frontline protesters.
He might just be making excuses for why he's not done editing.
There's that, but...
Well, so I guess the point is you have a podcast. It's called Titanium Physicist. There will be a new episode at some point.
We're on... Okay, the quarantine and resulting workload for my regular job meant I couldn't keep producing episodes monthly, so we're on quarantine hiatus, but we'll be out of it soon.
Cool. Well, thank you so much, both of you, for joining me to talk about all this stuff. This was a lot of fun.
Thanks for having me, Ryan. This was such a blast. I just like you kids so much.
Yay, Ryan.
Yeah, this was great. Long overdue.
Sure. I just loved being here. Thanks again.
You're welcome. Thanks, Ben.
No, thank you.
For showing up.
I love coming on your show, Ryan.
No, this was a good time. All right, well, thank you all for listening. Feel free to check out the show notes for this episode at sciencesortof.com, where we'll have links to a lot of the stuff we talked about. And with that, we will see you next time for a whole lot more science.
Sort of.
Visit sciencesortof.com for show notes, links to all the stories we talked about, and ways to interact with the hosts, guests, and other listeners. Science Sort of is brought to you by the Brachiolobe Media Network of podcasts, with audio engineering by Tim Dobbs of the Encyclopedia Brunch podcast. That's all for this week. See you next time on Science Sort of.
Press the plunger on the French press and then strain it out that way. So, similar.
French press.
Yeah.
I hear you talking about cowboys and French presses in the same sentence.
That doesn't compute for me.
But my French press is stainless steel. Does that make it manlier?
It's not about manliness. French people are plenty manly. It's just cowboyiness.
Cowboyiness.
There's not a lot of French cowboys. I think that's what I'm coming up against.
Yeah, you have Spanish cowboys, vaqueros, and the American cowboys, the buckaroos. Two types of cowboys, and one type of coffee.
The men who are part cow, the monstrosities.
Oh, yeah.
Don't forget them.
That's right. Yeah. Our Minotaur is the Minotaur a cowboy?
Cow man.
No, that's a bull boy.
Cow. Yeah. No, it's cow man.
Very manly.